Good morning friends. Today I am going to explain one of the important topic in thermodynamics, that is working of Carnots engine. Generally the question will be coming like this: describe the working of a Carnots engine and obtain an expression for it. That is, we have to calculate the efficiency. That is the expression for it. Here, before going to talk about the working of the Carnot's engine, first of all we should know what is source, what is sinks, what is insulating stand, and what is working substance. Working substance. If you don't know what is the source, sink, and insulating stand, we can't understand the whole topic. So first of all, we should know what is source. Source is what? A hot body, and which is maintaining a high thermal capacity and at a high temperature, that is T1 kelvins. And what is sink? Sink is a, generally we are taking as a cold body, or sorry, generally we are taking as a surrounding is the sink, and it is always at a lower temperature, that is T2 kelvins. Okay, source will be always high temperatures and sink will be always at low temperature. Now insulating system. So insulating stand means to make the whole system perfectly. A non-conducting stand is put on the base of the cylinder. So generally we have to take the cylinder like this. Here, cylinder in which this one is the cylinder and this is the piston and this is the gas is arranged in this cylinder. And next, to make the whole system perfectly non-conducting, a stand is put on the base of the cylinder. So that is called a insulating stand. And what is working substance? Working substance. The working substance is, generally we are taking as ideal gas, and this gas is enclosed in a cylinder piston arrangement. So these are the few basic points which we should have to know: what is source, what is sink, what is insulating stand, and what is working substance. Now come to the point, that is working of a Carnot's engine. In a Carnot's engine, the working substance is made to undergo a cyclic operation as shown in the figure. So the working substance is made to undergo the four cyclic operations, that is isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. So in your previous classes you have studied about what is isothermal process and what is adiabatic process. Isothermal process means in which the temperature remains constant. Adiabatic process means in which a heat is neither enter into the system and nor leave the system. And this diagram is, we are calling it indicator diagram. So generally in thermodynamics we are using the work done by the gas, work done on the gas by utilizing this diagram, that is pressure on the y-axis and volume on the x-axis. This particular diagram is known as the indicator diagram. Okay, so here working of the Carnot's engine is made to undergo a cyclic operation: isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. So first of all we will discuss about the first one, that is isothermal expansion. What is this one? So consider 1 gram mole of an ideal gas, or gas we can write, is contained in a cylinder. The initial state of the gas is denoted by A in the indicator diagram, where it has the temperature T1, pressure P1, volume V1. The cylinder is placed on the source and the piston is moved slowly in the upward direction. Here isothermally, that too. Here what we understood this one. Here let us consider 1 gram mole of an ideal gas which is enclosed in a cylinder piston arrangement, and this is represented by a position A in the indicator diagram, where the pressure P1, volume is V1, and temperature is T1, and this gas is expands slowly isothermally. Isothermally means heat is neither enter into the system nor isothermal means where the temperature remains constant. In this expansion, as the temperature is remains constant, pressure of the gas is decreases and volume is increases. Okay, so when this cylinder is placed on the it is placed on the source, first of all, in the first case we are going to put this on the source is always a hot body. Okay, so when it is placed on the source and the piston is moved in the upward direction, isothermal slowly isothermally, that is temperature is remains constant. Okay, and at the same time this is placed on the source, so that's why your temperature we should have to maintain constant now. So that's why the fall of temperature is compensated by the hot body. When it is placed on the source, that is fall of temperature is compensated by the temperature of the hot body. So that points I wrote here, that is here at this position pressure and volumes are pressure of the gas is decreased and volume is increased. Here it should be remembered, it's only for the note for your understanding purpose. Here remember that fall of temperature is compensated by supply of heat from the source. Initially we are placing the cylinder piston arrangement on the source in the first case. The final state of the gas is represented by the point B. Thus the isothermal expansion of the gas is represented by a curve AB. Okay, on the indicator diagram. Here this is the isothermal expansion curve, or we can write it is curve AB on the indicator diagram. So this is known as the isothermal expansion, where the temperature is T1, pressure is P1 and volume is V1. So here when the cylinder is placed on the source, so that's why pressure is, and the piston is moved in the upward direction, so pressure is decreases, volume is increases. Okay, so at the same time here because of that one the gas does some work done, so that work done we have to calculate. Let the quantity of the heat absorbed by the gas from the source is Q1. Okay, so the quantity of heat, so this is placed on the source first, so that's why the heat the gas from the source is Q1 is the equal to let the quantity of heat absorbed by the gas from the source is Q1. So the gas is taken some heat from the source, so that is Q1, and due to that heat the work is done by the gas to reach from position A to B. Okay, so that is the amount of work done W1 by the gas from A P1 V1 to B P2 V2 can be written as. So we all of you know that the heat energy is converted into a work done. So work done in terms of gases we can write work is what? Force into displacement. In terms of gases we can write in terms of pressure and change in volume. So from where to where? From this is V1 to the V2. So that's why V1 to the V2 we can write P dV. Now V1 to V2 P dV, PV is equal to RT. We can write PV is equal to nRT, or we can write for an ideal gas this is equal to 1, or we can write PV is equal to RT, or P is equal to RT by V. Okay, so this part we can P value is substituting in this equation. Then here temperature is T1 particularly. This is the ideal gas equation. Here we can write RT1 outside, then V1 to V2 1 by V dot dV. Okay, now if you integrate to that equation, then we can write Q1 is equal to W1 is equal to 2.303 RT1 log V2 by V1 if you substitute the limits. Then we can write 2.303 log E, log 10 value can be written as log E. V2 by V1, let us take this is equation number 1. Okay, now the situation second one is what? Adiabatic expansion. So at this position we should have to remove this cylinder from the source and it is placed on the insulating stand. So because we know that adiabatic process means a process in which heat is neither enter into the system and nor leave the system. So the cylinder is detached or removed from the source and it is placed on the insulating stand. Just now I told you what is insulating stand. So the piston is allowed to move further adiabatically. So initially in the first case, just the piston is moved up to this point where the pressure V1 and volume will be V1. So the next position adiabatically expansion, again the piston is moved in the upward direction. Okay, so in the upward direction. So where the temperature and volume will be different. So here the piston is allowed to move further adiabatically till the temperature of the gas is same as that of the sink. So generally sink is what? Sink is surrounding, where the temperature of the gas and temperature of the surroundings will be same. So till up to that point we should have to move the piston in the upward direction. So, hence the gas does external work done at the expense of internal energy. So at this position we are using this is non-conducting piston, no, sorry, insulating stand. In the second case this will be insulating stand, and here means that is heat is neither enter into the system nor leave the system, and the walls also a perfectly non-conducting. So at that position the gas utilizing some internal energy and does some work done when you move the piston in the upward direction. Okay, so that time we have to calculate the work done by the gas during the adiabatical expansion. So we know that work done can be written as P dV, and the situation is we have considered B to C. So the volume will be V2 to V3. So V2 to V3. Now we have to calculate this one. Now in adiabatic process we can write P V to the power of gamma is equal to K. Now we need the value for the P. So that's why P is equal to K by V to the power of gamma. Okay. Now V2 to V3 and P value is K by V to the power of gamma dot dV. Okay. If you take out the K, then V2, V3, 1 by V to the power of gamma dV. Okay. Now if you integrate to this equation and substituting the limits, then we will get V to the power of minus gamma plus 1 by minus gamma plus 1, and limits will be V2, V3. In the next case we will substitute the values of this one. We can write K is equal to V to the power of, here V to the power of 1 minus gamma plus 1. We can write 1 minus gamma. So V to the power of 1 minus gamma, and similarly this can be minus gamma plus 1 can be written as 1 minus gamma and V2, V3. Okay. Now take this K inside, then and substituting the limits also, then K V3 1 minus gamma minus K V2 to the power of 1 minus gamma by 1 minus gamma. Okay, so we know that K is equal to P V to the power of gamma, or at this situation if you substitute the value of K, then it will be equal to P3 V3 to the power of gamma, and at this position K will be equal to P2 V2 to the power of gamma. So we can write here P3, K place will be P3 V3 to the power of 1 minus gamma minus P2 V2 and to the power of, sorry, P2, this is gamma, P3 V3 to the power of gamma, P2 V2 to the power of gamma, and V2 to the power of 1 minus gamma divided by 1 minus gamma. Okay, now W3 can be written as here V3 to the power of gamma and V3 to the power of minus gamma get cancelled, and we will get P3 and V3 to the power of 1 means P3 V3 minus V2 to the power of gamma and V2 to the power of minus gamma get cancelled, and we will get only 1 V2 to the power of 1, or simply we can write V2 by 1 minus gamma. Okay, now here one more situation we can write here. We know that ideal gas equation is what? PV is equal to nRT. Okay, or PV is equal to RT. Then for ideal gas n is equal to 1. Now at this situation P3V3 is equal to the P3V3 is equal to the RT2, because here P3 and V3 will be at position of T2. So that's why we have to write it T2. And P2V2 will be equal to RT1. Here P2V2 will be RT1. Here P2V2 will be at this temperature, so T1. So if you substitute the value of P3V3 and P2V2 in this equation, W is equal to this is second work done. W2 is can be written as RT2 minus RT1 by 1 minus gamma. Okay, or we can write this one. T2 R is taken out. R T2 minus T1 by 1 minus gamma. Let us take this is equation number 2. So this is the work done by the gas by utilizing its internal energy. Now come to the point, that is third point, that is isothermal compression. So compression means, you know, the isothermally means that is temperature again remains constant. Now the piston is moved in the downward direction. Now compression, third position. So piston is moved in the downward direction. So the cylinder is separated from the insulating stand and placed on the sink. So now at this position we are going to remove the cylinder from the insulating stand, and it is placed on the sink, or generally surroundings are considering as the sink, where the temperature is T2 kelvins. Okay, here gas is compressed slowly. Now the gas is compressed. Move the piston downward slowly. So till the gas attains the state D. So till the gas is attains the position D, where the temperature where the work done here at this position, when you move the piston downward, here the work is done on the gas. So we have to calculate the third work done is work done on the gas. Okay, so initially two positions will be work done by the gas in isothermal process, isothermal expansion and adiabatic expansion. That will be the work done by the gas. Now here piston is moving downward, so that's why here work done on the gas we have to calculate. So for that purpose, work done on the gas can be written as W3, and similarly it will be here position P3, and this one at position D, the P4 V4 values are there. So that's why isothermal calculation already we did. So similar equation number 2 will be same, just like that equation we will get W3 is equal to RT2 log E V4 V3, and this can be written as one second. This W3 is equal to RT2 or log E V4 by V3. So this can be written as minus RT2. V3 goes up and V4 goes down. So that time we should have to write minus. And let us take this is equation number 3. Now adiabatic compression. So this is the final stage of the process where the cylinder is detached from the sink and placed on the insulating stand. So again we are using the insulating stand. So because it's a adiabatic process, so insulating stand we are using, that is heat is neither enter into the system nor leave the system, and the gas is compressed such that it undergoes a slow adiabatic compression till the state A is reached. So we should have to make the temperature from T2 to T1. Okay, we should have to compress till that. The work done W4 on the gases can be calculated. So we can write this is also adiabatic process. That is W4 is equal to V4 to V1 PdV, and this can be written as, this is opposite to that of the last second equation, minus of R T1 minus T2 by gamma minus 1. Now from equation number 2 and 4. So this equation number 2 is also related to the adiabatic. This equation number 2 is also related to the adiabatic expansion, and this is adiabatic compression. Fourth equation. So if you compare these two equations, we will get W2 is equal to minus of W4. Now from equation 1 and 3. So one equation is what, that is related to the isothermal. This one is related to the isothermal expansion, and this one is related to the isothermal compression. So if you compare these two equations 1 and 3, then we will get Q1 minus Q2 is equal to W1 minus W3. Now we have to calculate the efficiency. So efficiency is nothing but it's a total work done by heat absorbed by the engine. Total work done by the engine by heat absorbed by the engine. So that can be written as W by Q1. Heat is initially absorbed by the engine is Q1. Now work done by the gas in one complete cycle is, we have to calculate the 4 work done, that is W1 plus W2 plus W3 and W4. So we have to substitute the values of W1 value, W2, W3 and W4. So W2 and W4 are same, so that's why these are get cancelled. This is plus and minus. Now we will get here R T1 log E V2 by V1 minus R T2 log E V3 by V4. Now we have for simplification, just we have to make this this one is V2 by V1, and we should have to make this V3 by V4 is also V2 by V1. So for that purpose, just see the points B and C lie on the same adiabatics. B and C are lie on the same adiabatics. So that's why we can write in terms of temperature and volume, the adiabatic equations are T1 V2 to the power of gamma minus 1 is equal to T2 V3 to the power of gamma minus 1. So we can write T1 by T2 is equal to V3 by V4 to the power of gamma minus 1. Let us take this is equation number 6. Now again points A and D are also lie on the same adiabatics. Points A and D also lie on the, so this is isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. So here both A and D is also lie on the same adiabatic. So that's why we can write T1 in terms of volume and temperature, the adiabatic equation is T1 V1 to the power of gamma minus 1 and T2 V4 to the power of gamma minus 1. Then T1 by T2 can be written as V4 by V1 to the power of gamma minus 1. So this is, let us take equation number 7. Now we are comparing the equation number 6 and 7. So these two equation is also related to the T1 by T2 is equal to this much, T1 by T2 is equal to this much. So thus two we are equating. So when you equate these two equations, then V3 by V4 to the power of gamma minus 1 is equal to V4 by V1 to the power of gamma minus. So both the sides gamma minus 1 get cancelled. Then we will get V3 by V2 is equal to V4 by V1. So this can be written as V3 by V4 is equal to V2 by V1 we can write. Now from equation number 8 and 5 we have, so this is equation number 8 and next equation number 5, this one, this is 5. Now we got V3 by V4 is nothing but a V2 by V1. So simply we are substituting the equation number 8 in equation number 5. When you substitute this one, then we will get RT1 log E V2 by V1 minus RT2 log E V2 by V1. Okay. Now you take out as R RT1 minus T2 log E V2 by V1. Come. This is equation number 9. Now the efficiency definition already I told you, total work done by heat absorbed by the engine. So total work done, what we calculated, this much, or T1 minus T2 log E V2 by V1. Next, heat absorbed by the engine, this is nothing but a first equation. So initially first equation, that is already I wrote, this is heat energy supplied by the source due to which some work done is done by the gas, that can be equal to RT1 by log E V2 by V1. So by this equation we can write RT1 log E V2 by V1. Okay. So RR get cancelled, log E V2 1 get cancelled. Then we will get neta is equal to T1 minus T2 by T1 is equal to 1 minus T2 by T1 is equal to 1 minus Q2 by Q1. So this is the expression for the efficiency. Thank you. For more videos, subscribe my channel Physics.